Okay, solutions from liquid stock typically are solutions like concentrated ammonia in water or concentrated acids in water. And in making solutions from those stock, there are some cautions you need to be aware of. And I want to be sure that you understand these clearly. Let's say the solution you're given, say prep 500 milliliters, 0.50 molar hydrochloric acid, aqueous solution is what you're trying to do. Well, from liquid stock, what you'll need after this acid from the manufacturer is specific gravity in addition to everything else I just gave you. Because what you're trying to do from liquid stock is ask yourself how much or what volume, let's do it that way, what volume of liquid stock do you need? So that's the central question that you're asking. In the solid manufactured stock is what mass do you put in the beaker? Here, what volume do you need to extract and then dilute to the needed total volume? You can calculate that volume in milliliters needed is the same formula except divide by specific gravity. Molarity times volume in liters times formula weight of the solute, that'll be HCl, I'm showing you up here. Purity factor, that's the concentration of acid in the solution, divided by specific gravity. Now, specific gravity is equal to the density of that stock solution if it's in water, because specific gravity is a mass per unit volume. Anyway, this is density of manufactured stock in grams per mil. And so when you calculate everything, grams will cancel out, and you're left in milliliters, and you pipette that much, and you dilute it to whatever you need. So the purity factor here is the concentration of stock, of solute in stock, I should say. Okay, so we want to prepare 500 milliliters of 0.5 molar HCl. Well, on the assay label, or you may have to look it up in a what they call an MSD sheet, material safety data sheet. What's the specific gravity? Well, HCl on the average, specific gravity is 1.14. 1.14 times heavier than water. Well, and just put grams per mil on there. And so that's the density of your solution. Okay, so you're going to prepare 500 mils of this. Volume needed in milliliters, not grams, is molarity times volume. Let me go ahead and write the molarity in there. We want a 0.50 molar, and we want 0.500 liters. 36 grams per mole is the formula weight. Now, typically, you'll find it comes about 35 to 37%. We'll split the difference. And 0.36 is your purity factor. That is 36% active in HCl. It'll be on the label. It'll say HCl 36%. Specific gravity is 1.14 and then grams per mil. When everything cancels out, grams and moles and molarity and grams, all you're left with is milliliters. So we calculate this. Now, Now, this is a strong acid. Now, there's very, very important that you listen to me on this. Mixing solutions of strong acids. If you take a strong acid and put it in first and then pour water on top of it, it's a good chance it'll blow up in your face. It ionizes so fast and generates so much heat that it gets out of control, and that's not a good thing. So the preferred method is what we call A and W, acid into water, A and W root beer, if you recall that. Acid into water. So what you need to do is transfer a small quantity of water into mixing container. That's number one. Number two, slowly add needed amount, needed volume of strong acid and mix acid into the solvent. And three, then finally dilute to needed volume. So in the preparation we're talking about, we came up with 21.9 mils. So we need 500 mils. I'd say probably put 100 mils of water in the mixing container. And then two, add 21.9 milliliters of HCl 36% stock. And then three, and mix that. And then three, add solvent, which of course is your water, up to 500 milliliter total volume. So that keeps you from blowing your head off. But you put 22 mils of strong acid and start pouring water, it splatter back in your face, and that's a bad thing. Okay, solutions from lab stock concentrate. Down here at the bottom, this is what we're working on right now, this dilution equation thing. Molarity times volume equals molarity times volume. Okay, what does that mean? Typically, you have a concentrate on the shelf that you made. Like if you use instead of making solutions from HCl 36% all the time, you might make a 6 molar stock solution, put it on the shelf. And then you need 0.1 molar solutions for a lot of experiments or something. And so you'll figure out how much of that you need each time and dilute it. Okay, so it's a lot safer and a little more convenient. But here's the deal on the stock solutions. What I want to impress upon you is the calculation is based upon what we call the dilution equation. And it's derived from the definition of molarity, where molarity is equal to moles over volume expressed in liters. Now, what I want you to do is solve this expression for moles. Moles is equal to molarity times volume. Okay. Now, in making a solution, you start out with a concentrate amount, or no, excuse me, an amount of solute, and then you add solvent, and this gives you the solution. Now, one thing I want you to understand in this is that, say you had 1 mole of solute over here. You start with 1 mole, and then you add solvent on top, and you get your solution. How many moles of solute do you have over here? You have the same amount. You didn't change the mass number. You just changed the concentration. You have 1 mole of solute before and after, but you have different concentrations. You only diluted the amount. Now, what I'm trying to get to is moles before of the concentrate will equal moles after. And so that gives you your dilution equation. That is, moles of concentrate always equals moles of the diluted. In the diluted solution, moles in the concentrate amount that you use is still moles in the diluted sample. So if moles is molarity times volume, then we take molarity times volume of the concentrate is equal to molarity times volume of the diluted sample. And the question is, how much do you need to extract from your concentrate stock that you already know the molarity of to make whatever you need? You need this. This is your needed solution. Right there. This is a known because you made that deliberately and put it on the shelf. Got this big tank full of 5 molar HCl. So the question is, how much do you portion out and then pour all to make your needed solution? Let's say you're given stock concentrate of HCl that's equal to, say, 6 molar. Prep 250 milliliters of 0.75 molar HCl, aqueous solution. So the question is, how much of this 6 molar stuff do you need? Well, molarity times volume of the concentrate is equal to molarity times volume of the diluted sample. Well, you know the molarity is 6 molar. The question is, how much concentrate do you need? And molarity you're trying to make is a 0.75 molar, and you want to make 250 mils of it. Now, this is a special case. If the units are the same on both sides, or if you have milliliters on the left, milliliters on the right, you can leave them in milliliters. If one of them is, say, moles or grams that you're working with, the other side is molarity and volume you're working with, you have to go to liters. But if both sides have the same units, you can convert them to liters if you want to, but you know. We solve for your volume of your concentrate, and that's 0.75 molar times 250 mils divided by 6 molar. Right there, molarities drop out, and so this tells you how much of the stock solution you're going to. Okay, 31.25 milliliters is what I calculate. You see what I'm saying? Molarity times volume is moles before and after. But in the calculation, you're trying to find out how much of the stock you need. Then you'll transfer that volume of stock and dilute up to whatever needed volume you have. So here's your mixing. what did I say? 250 mils, yeah. Total volume. Move it up so you can see what I'm. So it's just showing you the protocol and mixing that. So if you'll look now. Should be page 2 in that handout I gave you. It should be page 11. It should be down at the bottom, but it came from that big package. Okay, first part is moles and molarity. Moles is a mass number. Molarity is a concentration number. Please keep that in mind. How many moles of HCl are in 35 milliliters of 0.55 molar HCl? So I'll show you. How many moles of HCl are in 35 milliliters, 0.55 molar HCl solution? Okay, so the question is, how many moles? Moles is always equal to molarity times volume expressed in liters. So look at the problem now. It says you got a 0.55 molar HCl, so 0.55 molar, and the volume is 35 milliliters. Okay, and so this is 0.035 liters. Molarity times volume in liters is what gives you the mole. And so now remember, molarity is moles over liters. So the liters will cancel out, and you're left with the moles as final. And I've got the notation up there: 0.0193, 0.0193 molar in HCl, aqueous solution. See how that works? Always convert molarity times volume. Some people call this solution data. Solution data means when you read a problem, you'll see these two numbers together, a concentration number attached to a volume number. Okay, let me show you how this, what these look like here. Zoom in on some of these. Oh, here's one. Okay. So you see right here, what volume of this is, let's see, reacts with 49.0 milliliters of 0.33 molar. See how those two are tied together in there? That's what I'm talking about. When you see those two, a molarity number and a concentration number put together, molarity times the volume, because you can convert that to moles. If you think about it, molarity is 0.33 times that in liters tells you how many moles of the sodium carbonate you'd have. So that's what I'm saying. You'll run into problems that have that, and we're going to work one out in very great detail and show you how the reactions work from solution data. That was that next one. All right. That was number 1. Okay. If 0.15 moles of sodium chloride in 125 milliliters aqueous solution, what's its molarity? Okay, you'll have a lot of these to deal with. Molarity, or a concentration number, is moles solute over volume of solution in liters. Yes? That's by definition. So what you're given here is 0.15 moles of sodium chloride and 125 milliliters, or 0.125 liters. And so you punch that in, and you get your molarity. So that's a 1.2 molar sodium chloride solution. Okay? What volume of 0.22 sodium hydroxide solution will contain 2.5 moles of sodium hydroxide. Well, you apply the same formula. Molarity equals moles over volume expressed in liters. Well, the problem says what volume is what we're looking for, this volume. So I need to solve that for volume, and it'll come out in liters in this case, is moles over molarity. So that's what it's asking you for. And so the volume in liters, 2.50 mole of whatever the solute is, sodium hydroxide, in a 0.22 molar solution. Well, that's moles per liter, if you remember. And so moles will cancel out, and you're left in liters, whatever that word is. 136 liters. So using the moles equal molarity times volume, you see how that kind of translates into several kinds of problems here. That last one here. What's the molarity of a solution prepared by 23.45 grams of sodium bromide in water to give 150 milliliters of aqueous solution? I give you the formula, weight 81 grams per mole. All right, now this is a very important one because you're going to need to do this a lot in some problems that are coming up. Okay, so we're given 23.45 grams of sodium bromide and prep 150 milliliter solution. Okay, so you're going to put 23.45 grams of sodium bromide in 150 ml of solution. Now watch what I do here. What's the concentration? Concentration in molarity, by definition, is moles over volume in liters, right? Okay, what I tell people to do is take your grams and divide by the formula weight and put it in the numerator like this. 23.45 grams over 81 grams per mole. See the numerator? And that gives you the moles right away on the top of that expression. The volume expressed in liters, you move the decimal 3 places to the left, 150 liters. Grams will drop out, and you're left with moles over liters or molarity. And 1.93 molar. See how I do that? So you've got a mass going into a volume, but you need to make the conversions kind of intuitively as you go along. And you can just, and you get it to your concentration terms very quickly. Okay, number 5 says, what is the molarity of an aqueous solution if 0.2074 grams of potassium hydrogen phthalate, that's a standard, is dissolved in enough water to give 100 milliliters of aqueous solution? And I give you the formula mass, big molecule kind of thing. Okay, so molarity is equal to moles over volume in liters. So we do the same thing here that we did in the previous problem. We got 0.2074 grams of KHPH, and it's 204.22 grams per mole. So that will give you the moles that we need on the numerator of our definition. And we're going to dilute it to 1 liter, 100 mils, or 0.100 liter. And so that works out to about a 0.10 molar in the KHPH solution, aqueous solution. So always think in terms of moles per liter. Now, if you're given the concentration and volume, and you need moles, molarity times volume. Very, very important concept here. Okay. Now, here it's asking how many grams of reagent grade KClO3, potassium chlorate, would be needed to prepare 250 milliliters of 2.25 grams aqueous solution. We'll give you the formula weight and the purity of the stock. Well, remember, it's asking you for grams. How much do you have to extract out of the manufactured stock? Well, the formula, grams, is molarity times volume times formula weight over the purity factor. That's number one. Okay, what does it say? You need 250 milliliters of 2.25 molar. Okay, so I need 2.25 molar solution. And it says I need 250 mils. In liters, that's 250 liters. And the formula weight is 122.56, 122.56 grams per mole. That is divided by the purity factor, and it's 1.00. Remember, purity factor is a decimal fraction. So punching those numbers in, it says 68.94 grams. That looks more like an 8. Okay, how do you make your solution? You transfer 68.94 grams of the KClO3 into the mixing container and dilute up to, but not to exceed, 250 mils total. They make special flasks that are exactly calibrated for 250 mil kind of thing. So, you know, you can be very accurate on some of these. All right, a solution of sodium acetate is prepared by mixing 135 grams of impure manufactured salt into enough water to make 225 mils of aqueous solution. The assay purity of the reagent is 96.2% by weight. How many grams of pure salt is mixed into the solution? And it gives you the formula weight like that. It's the same thing. You're looking for grams of sodium acetate, and that's your molarity times volume times formula weight over your purity factor. And then you need to express that purity factor in decimal fraction this time. Let me move it up here so you can see what's going on. Okay. We got 135 grams of impure, so manufactured salt. Into enough water to make 225 milliliters of reagent. Assay purity. Oh, it's how many grams of pure salt is mixed into the solution. There's a little bit more involved here. Okay, I'm sorry about that. We get that. You got 125 grams. Okay. No, 135 is what it said. I'm sorry. 135 grams of the salt. And the molarity of that is not known. So molarity is moles over volume, and you got 225 mils, so that's 0.225 liters. Okay, so there's your molarity number right there. Already got the 225, 0.225 liters. That's going to cancel on us. All right. Okay, that's fine. 135 grams pure manufactured salt, enough water to make 225 mils of the aqueous solution, 225. So there, that's it. Moles. Okay. The assay purity is 96%. Formula weight, did I give you that? Yeah, 82.03 grams per mole. And the assay is 0.962, like that. Now, moles is mass in grams over formula weight, like that. So it's kind of an intuitive problem where you have to kind of substitute some stuff together to make things fit. I'm going to solve this out for moles first. So moles is equal to product divided by all that other stuff. This will cancel. So that would be 135 grams times 0.962. So those two go together. And then I can come in here and divide this out by 82.03 grams per mole. Grams will drop out. And so the moles of solute out of this is 1.58 of the sodium acetate. Okay? Now, that is equal to, like we were saying, mass over formula weight. So this is what you have here, and so that is mass in grams over formula weight. And the formula weight is 8203. Well, we put that back in there. And so we need mass, don't we? Mass is equal to 1.58 mole times whatever that formula weight, 82.03 grams per mole. So it looks like we're just kind of going in circles, but you got to deal with stuff like this. Times 82.03, and so there are 129, 130 grams of the sodium acetate added to the making up the solution. So you're going to have to intuitively calculate some of these based on the definition. There's nothing in here you couldn't handle. We started with grams and recognized this as mass over formula weight. I went to moles, and then I took moles equal and then study the problem, and it'll work out. Okay, so number 3 here is, say you're given $63.2 grams of lithium hydroxide, okay, and assume 100%, and the molarity, actually aqueous, let's see, hydroxide, so that's a solid, and solution molarity is equal to 1.55 molar. Okay, so molarity, moles of solute over volume of solution. Okay, so we got 1.55 molar, and they want to know what volume. So this is our unknown right here. And so molarity now, that's just 1.55 molar. Moles is 63.2 grams. 23.95 grams per mole. So there's your mole divided by the volume, and that'll be in liters. So you just kind of punch that in, and volume in liters now is 63.2 divided by 23.95 and 1.55. Now this one's going to come out in liters. We want it in milliliters, 1.68. And so you punch it in, it should be 1.68 liters in that particular one. Okay, I'm trying to beat the clock here. So all I did here is use the idea of, well, molarity is moles over volume in liters. And think in terms of, well, what are they asking for? Liters. Okay, so I went straight to that based on the data. Now, the basis of this, of course, is the volume of stock needed. Is also molarity times volume in liters times formula weight of the solute. Purity factor, that's your concentration in the manufactured stock, solute in that stock. But you have to put in specific gravity, which is the density number this time. And we're usually working only with strong acids, and it'll have the specific gravity on the label for you. Okay, let's see what we got here. Well, aside from the safest practice, you remember A&W, root beer, add the acid into a small quantity of water and then dilute. All right, number 2, let's go on down here. What volume of stock, 37%, will be needed to prepare 100 milliliters of 3 molar aqueous solution? Okay, given prep 100 milliliters of 3 molar HCl from HCl 36%, and we'll use 1.14 and 36 grams per mole, like that. So it's really volume in milliliters, again, is molarity times volume times formula weight, very straight, purity factors, and specific gravity. And so we're looking for a 3 molar, and we're looking for 0.100 liters. 100 mils goes to 0.1 liter, 36 grams per mole, and purity factor 0.36. That's what the concentrate of the solute, from manufactured solute, and 1.14 specific gravity is in grams per mil. And punch those in, you come out with, looks like you got 25.6 milliliters. Now, that's the absolute amount, okay? You need 3 molar. So if you tried to pour water on top of that, it would be very dangerous, bottom line. So what do? Well, if you're trying to make 100 mils, that's going to eat up about a quarter of it real quick. So you probably want to take about 25 or 30 mils and then add that on top, because you don't want to take half of it or 75 mils and try to pour that in. You'll exceed the total volume you have. So you want to be careful. That's why I built this problem like that. So, move it up here, mixing. 1, to approximately 25 to 30 milliliters of water, add 25.6 milliliters of HCl 36%. So you want to slowly add that in that, because you take 25 and say 25, that's 50 mils. All right, then you can dilute it to the 100 without exceeding everything. But if you started with 75 mils, then pour that on top, you'd be too much. Okay, and 2, add solvent up to 100 milliliters total volume. So that's the point. The point is, try to figure out how much water you will need to start with, so that when you add your acid in, you won't, and then dilute, you won't overshoot everything. Okay. Okay, 50 milliliters of concentrated nitric acid is used to prepare 2 liters of 5 molar aqueous solution. Okay, number 3. Okay, what we're given here is 50 milliliters of HNO3, 68% stock, for 2.0 liters of 5 molar aqueous solution. What's the molarity of the manufactured stock? Is your unknown here. Okay, so if you work from the definition I gave you on what volume would you need, all you need to do is solve that for molarity. Like, volume needed in milliliters is molarity of your final solution times volume in liters that you're trying to make. This is what you're prepping, formula weight over the purity factor. And did I give a specific gravity? 1.42. And then specific gravity. Okay, so we want to solve that for molarity. If you want to do it this way, volume in milliliters times purity factor, fraction, specific gravity, divided by volume in liters times the formula weight. Like that. So you use the same formulas, but you might need some other kind of calculation. Like in this case, you're calculating a molarity. So let's see. If you decided to use 50 milliliters of your stock, and its purity factor is 0.68. Specific gravity is 1.42 grams per mil. And the volume, 2 liters. There we go. And the formula weight of nitric acid, did I put that in there? I'm going to put it in there. Well, I didn't put it in there. So what is that? HNO3 has 48, 14, and 1. 12, 13, 4, 5, 63. Okay. 63 grams per mole. Okay, so what's your molarity? It'd be moles over liters. So that's what will happen. You get rid of grams, milliliters, and milliliters, you'll have moles over liters left. And so you punch all that into your calculator, and I don't think I punched it in. 22.5 molar. Somebody punch that in and see what it looks like.
We're given the final solution. We have to find the molarity of the manufacturer's solution.
2 liters was the final solution.
Yes. We have to find the molarity of the manufacturer's.
Oh, that's manufactured.
Yes.
Yeah, okay. Oh, okay. What was the manufacturer's like? I'm losing track of my own problem. Anyway, 22.5 molar. That's some nasty stuff, guys. Anyway, here we go. Okay, what volume of water must be added to 30 milliliters of 5 molar calcium chloride solution diluted to 1 molar calcium chloride solution? Now, this is a molarity times volume of the concentrate equals molarity times volume of the diluted sample. Now, it's got a little twist in here. It says, how much water do you pour on top of the concentrate to get to the final volume? Well, you already have in your problem, this is the point to be made, you already have 30 mils, so you're going to have 30 plus whatever solvent on top of it. But when you use this dilution equation, you're going to get the volume of the final solution total. So watch what happens here. Okay, what volume of water must be added to 30 milliliters of 5 molar calcium chloride? Okay, so you have 5 molar and 30 mils, both sides. And you need a 1 molar solution, volume of the solution. Now that's 30 mils plus the solvent. So you solve for your volume of solution, it'll come out in milliliters. So it's 150 milliliters final volume. Molarities will cancel out. However, you start with 30 milliliters of lab stock, which means you subtract that out of the 150, because the 150 represents the final total volume. So if I subtract that off, all I need to add is 120 milliliters of solvent water needed. Because, see, you're starting with the 30 mils already, and you want to stop at 150. Because it's asking you to make what volume of water must be added to 30 to get it down to a 1 molar solution. See what I'm saying? And so you want to be careful that you already start with 30 mils. And then but the dilution equation gives you the final total volume. That's solution volume right there. Is everybody kind of understand what I'm saying here? Because that does show up on the exams. So be careful there that you understand. Okay, this last one in there real quickly. Given, okay, so we got 60 mils of water added into 80 milliliters 2.5 molar hydrochloric acid stock, aqueous stock. What's the concentration of HCl solution after mixing? Well, that's simply molarity times volume of the concentrate is equal to molarity times volume of the diluted sample. So we're adding 60 mils to 80 mils. So our final volume is 60 plus 80 mils, 140 milliliter final volume. Okay, and so we need to calculate the molarity. Well, you started with 60 mils of, no, that 60 mils was added to the 80 mils, excuse me, 80 mils of 2.5 molar. And so we put the 140 in there and then solve for your molarity. So molarity now is molarity times volume of the concentrate over the volume of the solution, diluted solution. So that is 2.5 molar times 80 mils over 140 mils. Mils drop out. And so punching that in will hopefully give 1.43. I'm going to check it. .43, yeah. So that gives you that final concentration, 1.43. Now, guys, y'all got to work at this level. So, you know, try to figure out how to apply the definitions and manipulate them and so forth. Take the data and what's given, and then think in terms of what's needed, and manipulate the equations as the problem would dictate.